Our second method for finding oxidation states is what's called total accounting. Now, total accounting works by figuring out the difference in the number of electrons you started with versus the number of electrons you finished with. So what we had to consider with total accounting is how many electrons are getting from bonds, how many electrons are getting from lone pairs. Now, this is different than something like relative accounting that only considered the electrons you gain or lose through bonding. The upside of total accounting is that it will always work, regardless of whether or not you have an ion. But it is a much more time-intensive procedure. But you're going to start out the same way when you do total accounting, and that is you're going to draw an arbitrary circle around your atom of interest. Now, unlike before where we only considered the bonds, what we're going to do here is we're going to say that our oxidation state equals the number of valence electrons you started with. In the case of nitrogen, this is 5 valence electrons. We're going to subtract off how many electrons we have on the central atom. So in this case, we have 2 from this lone pair. Now we need to start going around the circle. And as we move around the circle, we're going to add 2 for every bond where nitrogen is more electronegative than what it's bound to. Add 1 for every time nitrogen is bound to another nitrogen atom, and we're not going to add anything where we're bound to something where nitrogen is less electronegative. So we come to our first nitrogen-oxygen bond, we don't get anything. So we're going to subtract 0. Moving along, we hit our second oxygen-nitrogen bond. We have nitrogen less electronegative than oxygen, so again we're going to subtract off 0. Keep moving along, we'll hit the second nitrogen-oxygen bond, subtracting off 0, nitrogen is less electronegative. We work our way around, we get 5 minus 2 minus 0 minus 0 minus 0 will give us a plus 3 oxidation state for nitrogen. So now let's do oxygen. So if we take this doubly bound oxygen, oxygen starts out with 6 electrons. We have 2, 4 electrons in terms of lone pairs. As we start working our way along, our first nitrogen-oxygen bond, oxygen is more electronegative than nitrogen, so we're going to subtract 2. Hit our second nitrogen-oxygen bond, oxygen again is more electronegative than nitrogen, so we're going to subtract off another 2. And now we're out of bond. So we got 6 minus 4 minus 2 minus 2 gives us oxygen and a minus 2 oxidation state. What about this other oxygen? Again, we draw our circle. We have oxygen. It starts out with 6 electrons. We now have 2, 4, 6 electrons in terms of lone pairs. And as we draw an arbitrary starting point, work our way around, we only have 1 nitrogen-oxygen bond. Oxygen is more electronegative, so we're going to subtract 2. We get oxygen again as a minus 2 oxidation state. Now if you compare this to something like relative accounting we didn't care about the lone pairs, so we just started here and worked our way around, we'd only have oxygen at minus 1 oxidation state. The reason why this works and relative accounting doesn't is that when we drew the Lewis structure of NO2 minus 1 of nitrite, we had to take our extra electron, that minus 1 charge, and put it here on this oxygen. So what about atoms bound to themselves? So let's draw the structure now of ethane. In this case, both carbons have the same oxidation state, so we're only going to worry about one of the carbons. We're going to draw our circle. We have carbon, starts out with 4 valence electrons. It doesn't have any electrons in terms of lone pairs. Now we're going to take our arbitrary starting point. So we go along, carbon is more electronegative than hydrogen, so we're going to subtract off 2. Second carbon-hydrogen bond, subtracting off another 2. Now when we get to the carbon-carbon bond, we're only going to subtract off 1. The reason is that this bond consists of 2 electrons, 1 donated from each carbon. Well, carbon's not more electronegative than carbon, so the best they can do is pull their electrons back out. In this case, we're going to have a minus 1. Work our way around. One last carbon-hydrogen bond will give us a minus 2. And then when we finish up, we have 4 minus 2 minus 2 minus 1 minus 2 will give us carbon and a minus 3 oxidation state.